Hey everyone, and welcome. Today we are pulling back the curtain on this incredible, hidden world of chemistry. Seriously, it's the science that powers the green in leaves, the deep red in your blood, and some of the most powerful industrial processes on the entire planet. So, let's dive right in.
So, right off the bat, here's a question for you. What on earth is the connection between these things? They seem totally unrelated, right? Well, the answer lies in this fascinating kind of molecular teamwork, where metal atoms act like captains, assembling a whole team of other molecules around them to get these amazing jobs done. Okay, so to really wrap our heads around how this all works, we first need to meet the main players in this chemical story, the metal complexes themselves. These are the fundamental building blocks.
At the very heart of our story is something called the coordination complex. Now, the easiest way to think about this is like a sports team. You've got your central metal atom, that's the team captain. It's a Lewis acid, which is just a fancy way of saying it's looking to accept electrons to build out the team. And then you have the ligands. These are the specialized players surrounding the captain. They're the Lewis bases, bringing their skills, in this case, donating their electrons to form a really strong bond with that metal.
So, you might be wondering, what makes these complexes so special compared to something simpler, like a double salt? Well, here's the key difference. When you dissolve a double salt in water, the whole thing just breaks apart. The team completely disbands into its individual ions. But a coordination compound? Totally different story. That core unit, the metal and its ligands, which we call the coordination sphere, it sticks together. The core team stays intact no matter what. And that's precisely why they have such unique and stable properties.
All right, so now that we've met the players, let's dig a little deeper. It's time to understand the rules of the game. How do these atoms actually bond? What kind of shapes do they form? And maybe the coolest question of all, why do they produce such vibrant, incredible colors?
The first real attempt to explain all this was something called valence bond theory, or VBT. It was proposed by the absolute legend, Linus Pauling, and he imagined the bond as a pretty simple overlap. The ligands had filled orbitals of electrons, the metal had empty ones, and they just kind of came together. It was a really good start, a solid first draft of the rules, but it turned out to have some pretty serious blind spots.
Yeah, the problem was VBT just couldn't explain the most fascinating stuff. Why are these compounds so ridiculously colorful? Why do some of them act like tiny little magnets? VBT was totally silent on these questions. It became pretty clear that we needed a more advanced playbook to figure this out.
And that advanced playbook is crystal field theory, or CFT. This model takes a completely different perspective. It basically sees the ligands as simple points of negative charge. Now, as these negative points get close to the metal, they start to repel the electrons in the metal's own d orbitals. And this repulsion isn't uniform. It actually splits the d orbitals into different energy levels. And believe it or not, that splitting, well, that's the key to everything.
So here's how it all connects to color. Different ligands, our specialized players, have different strengths. A strong field ligand causes a big energy split between those d orbitals. Now, for an electron to jump that huge energy gap, it has to absorb high-energy light, which is stuff like blue or violet light. What our eyes see is the complementary color that's left over, in this case something like yellow or orange. On the other hand, a weak field ligand causes a tiny split, absorbs lower energy light, and gives us a completely different color. The ligand literally determines the color of the team's jersey. It's amazing.
Now, let's switch gears and look at a very, very special class of these complexes. We're talking about a group of all-stars where the metal decides to team up directly with carbon. And this simple connection opens up an entirely new field that actually bridges the gap between two major areas of chemistry.
And these are the organometallic compounds. Their one defining feature is that direct metal-to-carbon bond. It's this unique partnership that marries the world of inorganic metals with the world of organic, carbon-based molecules. And the result is compounds with some truly extraordinary properties and uses. So how do we predict which of these organometallic teams will actually be stable? Well, it turns out that for many of them, there's a kind of championship rule they like to follow. It's a lot like how simple atoms are stable with 8 valence electrons. You probably remember the octet rule. Well, many of these transition metal complexes are most stable when they have a grand total of 18 valence electrons.
So how do chemists actually know if a team is stable? Well, they've got a system for counting up the total number of electrons in play. You start with the metal captain, in this case rhenium, which brings 6. Then you add up the electrons brought in by each ligand player. 2 from this one, 4 from that one. And as you can see, when you add it all up for this complex, boom, you land on that magic number, a perfect, stable 18.
Okay, this is all fascinating theory, but what's the payoff, right? What does it all mean?
Well, let's move into the real world and see how this hidden teamwork has a massive impact on our daily lives, our industries, and even our technology.
And let me tell you, these compounds are true workhorses. We use them to literally pull precious gold and silver out of raw ore. They act as incredible catalysts to speed up critical chemical reactions. They were even the key to old-school photography. From softening the water in your home to making the chrome on a car look perfectly smooth, their teamwork is absolutely everywhere.
And what about those organometallic all-stars? Oh yeah, they're just as powerful. They're used to create the ultra-pure nickel needed for electronics, and they serve as catalysts for making all sorts of everyday chemicals. They can make our fuel burn better, and, in an absolutely amazing twist, a derivative of ferrocene has been turned into a powerful anti-malarial drug called ferroquine. How cool is that?
But really, the most fundamental application of all isn't in a factory or a lab. It's inside of us, and it's all around us. So let's bring this discussion right back to where we started, to the blueprint of life itself.
This is just beautiful. Here we can see how nature uses the exact same basic design for two completely different, absolutely vital jobs. Both chlorophyll and the heme in your blood are built around this gorgeous ring structure. But just look at the center. Chlorophyll has a magnesium ion. Hemoglobin has an iron ion. That one simple swap of the team captain, it changes everything.
And the role of that magnesium ion is just ingenious. See, without it, the ring would just absorb sunlight and instantly flash it away as wasted light. But with magnesium sitting there in the center, the complex becomes phosphorescent. That means it holds onto that solar energy for just a fraction of a second longer, just long enough for the machinery of photosynthesis to grab it and put it to work, turning sunlight into life.
And in hemoglobin, the story is just as amazing. An iron ion, left on its own, would react with oxygen and get permanently stuck. It would essentially rust, becoming totally useless for transport. But the huge globin protein that surrounds the heme group acts like the perfect bodyguard. It protects that iron, allowing it to gently pick up an oxygen molecule in your lungs and then release it in your tissues over and over and over without ever being destroyed.
So, from the basic rules of bonding that create brilliant colors, to the industrial powerhouses that build our modern world, and finally to the very molecules that make life possible, the principles of coordination chemistry are a true masterclass in teamwork. It really makes you wonder, what other invisible chemistry, what other incredible molecular teams are out there shaping our world in ways we haven't even begun to discover?